For my lab report, I decided to record a car driving through the Techwood-Bobby Dodd intersection at a constant velocity. I uploaded the video to Tracker and then cut the video down to the relevant portion. I first used the calibration stick to reflect the length of the car, which according to Google is about 3 meters. Next, I adjusted my axis, arbitrarily moving the origin to the car's taillight and rotating the axis so the car would move in the positive X direction, with negligible motion in the Y direction. If I had made the car travel in the negative X direction, the ball in my computational analysis would have moved in the opposite direction away from the origin, and my graphs from both Viddal and VPython would be reflected over the x-axis. However, the magnitude of the velocity would stay the same. If I had not slanted the axis, I would have had to have dealt with velocity in both the x and y directions. I estimated the center of mass to be below the front door handle, so I marked it in each frame to track the car's movement. Tracker made a table of the corresponding time and position values, which I then exported to Excel so I could later make a scatter plot. I then worked on making a computational model. I plugged in the mass of the car, about 1,400 kilograms. Then I plugged in the initial position of the car, which I found in Tracker, and determined the ball's initial velocity. The initial velocity and average velocity are equal because there is no net force acting on the car, so velocity is constant. I used Tracker's values for the final and initial positions and divided the displacement by change in time, which I also found in Tracker, to get the value of the initial velocity. I changed the time to less than 2 because the duration of the video was just under 2 seconds. The net force is 0 because the velocity is constant. It is impossible to say whether forces acting on the car, such as friction, cancel out because the velocity only indicates that there is no net force. I substituted equations from the momentum principle into the code to predict the new velocity and position of the car. I then uncommented parts of the code to write a .csv file. The ball moves along the positive x-axis and the car's position versus time is plotted. Once I opened the .csv file in Excel, I plotted both the values from Tracker and the values from the computational model on the same scatter plot. As you can see, the trend and values are very similar, and the values from Tracker barely diverge from what the computational model predicts. However, slight discrepancies could be accounted for by the presence of external forces that I assumed to be negligible when making the computational model. Using the momentum principle in VPython, I was able to accurately predict the change in position of the car with respect to time.